everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see the problems on the noise parameters. In the earlier session, we have defined noise parameters like noise power spectral density, noise equivalent bandwidth, noise temperature. In this session, we will see some more noise parameter mathematical definitions and we will apply the same concepts for solving the problems. At the end of this particular session, student will be able to learn two learning outcomes. The learning outcome 1 is mathematical definition of noise parameters, and learning outcome 2 is we will apply the concepts in solving the problems. So, the one more important noise parameter which is very useful in the analysis of noise, that is nothing but noise figure. Noise figure is mathematically defined as input signal to noise ratio to the output signal to noise ratio. So, noise figure in decibels is expressed as 10 log 10 f. So, the significance of this noise figure is, if the noise figure value is 1, it indicates that the system have no noise, and if noise figure is 0 decibels, in terms of decibels, if it is 0 decibels, it indicates that there is no noise in the system. So, this is a very crucial parameter to understand the noise in the system. Based on the mathematical value of the noise figure, we can say the system is noisy or less noisy. So, if f is very less, the system is less noisy, f is more, the system is more noisy. So, for a cascaded set of amplifiers, the noise figure is also mathematically represented as f total is equal to f1 plus f2 minus 1 by g1 plus f3 minus 1 by g1 g2. So, where f1, f2, f3 are the noise factors or noise figures of each stage, and g1, g2, g3 are corresponding gains. Similarly, equivalent noise temperature also can be calculated using the formula for cascaded stages is T is equal to Te1 plus Te2 by g1 plus Te3 by g1, g2. So, we will see the problems related to this cascaded stages of amplifiers and also we will see how to compute the noise figure mathematically. So, an electronic system has an amplifier followed by a mixer stage. So, the first stage is mixer, later on an amplifier is there. So, these are the obvious blocks in any communication system. The noise figures of amplifier and mixer are given. So, this noise figure of amplifier is 20 dB, the noise figure of, let us say this is f1, f2 is mixer is 30 dB, f1, f2. So, we are asked to compute the overall noise figure. So, the overall noise figure for a two-stage amplifier is f is equal to f1 plus f2 minus 1 by g1. So, f1 is the noise figure of the mixer. So, the mixer value is given in terms of decibels 10 log 10, 10 log 10, f1 is equal to 30. From this f1 is equal to 10 cube. Next one is 10 log 10, f2 is equal to 20 dB, f2 is equal to 10 square. Given the power gain of the amplifier, is G1, G1 is equal to 10 log 10 is equal to, we will get 10, 10 log 10 gain is equal to 10, from this we will get gain as 10, G1. So, f is equal to f1 plus f2 minus 1 by g1, f1 is 10 cube, f2 is 100 minus 1 by g1 is 10. So, we will get the overall noise figure is 1010 approximately. To convert into decibels, what we need to do? We need to apply 10 log 10. So, in terms of decibels, it is 3043 decibels. So, one more receiver is given. So, a receiver has two stages. From the first stage, the noise figure is and corresponding gain is given. In the second stage, noise figure gain is given. They are asking us to calculate the total noise figure. So, the total noise figure f2 is equal to f1 plus F2 minus 1 by G1. So F1 is 2, F2 is 3, G1 is 10. So 2 plus 2 by 10 will get 2.2. Noise figure in decibels, if I want to convert into decibels, apply 10 log 10. In terms of decibels, its value is 3.4 decibels. One more problem is given in terms of two-port network. A two-port network is given to us. The noise present at the input port of two-port network is Ni is equal to 5 microwatt. The noise figure is F is equal to 0.75 and the receiver gain is 10%. They are asking us to calculate the available noise power by the two ports. So, this is input noise. GA is equal to 10 power 7 the receiver gain and NA is, so after going through the two port network, the output noise power is N0 is equal to G into Ni. So you will get the output noise power as 50 watts, the output noise power of the two port network. So we know that the noise figure also can be expressed in terms of noise powers, applying that F is equal to Na0 by Naos. So solving, we will get the noise figure value in terms of decibels is 0.75 decibels. So the available noise power by the two ports is 1.118 into 50. The output available noise figure is the difference between the overall noise figure minus 50 input noise figure. So we will get 9425 watts. Next, this is a cascaded system. Temperatures are given. The temperature of first system is 250 Kelvin, second one 400 Kelvin, third one 900 Kelvin. If the available power gain at the second stage, that means G2 is given 10. What gain must the first stage should have to guarantee to an effective noise temperature? Given the overall noise temperature, now we need to compute the gain at the first stage G1. So the overall noise temperature is TE is equal to TE1 plus TE2 by G1 plus TE3 by G1 G2. Substituting overall noise temperature at stage 1, noise temperature at stage 2, noise temperature at stage 3, and G2 is also given, that is 10. So the formula is TE1 plus TE2 by G1 plus TE3 by G1 G2. Substituting the G1 value or the gain at the first stage is 16.33. We need to maintain minimum gain of 16.33 so that it will guarantee an effective noise temperature of 280 degree Kelvin. So this gain should be maintained in the cascaded connection in order to get the final value of noise equivalent temperature as 280 degree Kelvin. Next problem is given, this is based on the noise figure. An engineer uses an amplifier to amplify the output of antenna whose temperature is given. What is the effective input noise temperature of the amplifier? So the spot noise figure is given 10 dB. Using that, converting the spot noise figure into linear scale, its value is 10. The noise equivalent temperature F minus 1 into T0, we will get 2610. The spot noise figure formula is F is equal to 1 plus TE by the standard temperature, we will get 14.05. This is the spot noise figure. Now effective input noise temperature and operating noise, effective noise temperature is TE and the operating noise figure is 14.05. So this is a problem which is based on the three-stage network. G1, F1, G2, F2, G3, F3 is given stages wise. The gains and noise factors are given in terms of decibels. First we need to convert the decibel scale into the linear scale for the calculation. So as per Frisch formula, F total is equal to F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1 G2. So F total we will get 9.5948. In terms of decibels, 4.14 dB. Applying 10 log 10 F, we will get 4.14 dB. Next, the noise equivalent temperature formula is TE is equal to T1 plus T2 by G1 plus T3 by G1 G2. So, the noise temperatures are given, that is 200 for stage 1, 400 for stage 2. Stage 2, the linear value of the gain is 10. Stage 3, 600 Kelvin, G1 G2, 10 into 15.85. So, the equivalent noise temperature is 243.78 degree Kelvin. Again, a 3-stage amplifier is given. Here, instead of giving every time noise figure, temperature is given, and they are asking us to compute the overall noise figure, overall noise temperature. So, from this given data, we will convert first them to a linear scale. So, 10 log 10 f is equal to 18, f or g is equal to 18, G1 is equal to 10 power 18 by 10. Similarly, G2, G3, 10 power 12 by 10, 10 power 15 by 10. The corresponding G1, G2, G3 of the individual stages of amplifier is calculated. Later on, first we need to convert the noise figure to the temperature. Noise figure given for stage 1 converted into linear scale, it is 1.78. So, at the stage 1, the noise equivalent temperature is F1 minus 1 into T. T is the room temperature. Similarly, for stage 3, F3 is given, T3 is calculated 864.2 degree Kelvin. The overall noise figure, so the overall noise equivalent temperature is T1 plus T2 by G1 plus T3 by G1 G2. So, substituting all the values, the equivalent noise temperature is 232.61 degree Kelvin, and the noise figure, overall noise figure is 1 plus TE by T. So, 1 plus 232.61 divided by 290. The effective value of noise figure is 1.802. In terms of decibels is 2.55 dB. So, in this session what we have seen is, we have defined the noise parameters like noise figure, which is very important parameter, and also we solved the problems which relates the noise figure and equivalent temperature. For particularly we concentrated on the cascaded stages of amplifier, and also we solved the problems on the noise parameters for cascaded stages. Thank you.